In the last lecture, we discussed atomic number and mass number of nuclei. Atomic number is the total charge, total units of charge on the nucleus, and mass number is the total number of nucleons in the nucleus. Atomic number determines the chemical properties of the nucleus. And then we defined the atomic weight of a nucleus, which is the weighted average of the mass number of all the isotopes of that nucleus. Then we discussed the size of the nucleus. We found that the radius of the nucleus is proportional to the mass number raised to power 1 by 3. And then we discussed the nuclear stability of nuclei. You see, we have protons and neutrons. Protons repel each other, neutrons attract each other, and the balance between the number of neutrons and protons determines the nuclear stability. And if the nucleus is not stable, then it emits alpha and beta particles and also the gamma radiation. And then we discussed some schemes of decay. For example, here rhodium 107 decays by emitting a beta particle and leaves the daughter nucleus in an excited state, and then the nucleus comes down to the ground state by emitting a gamma particle. So, this is what we did last time. Today we discussed the stability of the nucleus. We shall now quantify the stability of the nucleus. You see, we know that a stable nucleus is one which does not decay into a different nucleus. It is obvious that nucleons in the stable nucleus are bound to one another. You see, there are 4 nucleons in this nucleus, and if they are bound together, then the nucleus would be stable, otherwise it would be unstable. That is, they must come together and get bound to each other in this shape. In the process of binding, they emit energy. They emit energy in the form of photons, and the nucleus then becomes stable. So, nucleus becomes stable by emitting the photons, emitting the energy. It is just like the gravitational field. You see, when a particle falls into the gravitational field, it loses energy. Similarly, here 4 nucleons, when they bind together, they lose energy, and it is this energy which is lost gives us an idea of what a stable nucleus would be. Now, according to the Einstein's equation, you know, energy is equal to mc square, and the loss of energy that we talked about, the loss of energy when they bind together these nucleons, the loss of energy means loss of mass according to the Einstein's relation. So, the difference between the combined mass of the nucleons and the mass of the nucleus is called the mass defect. You see, these 4 nucleons, they have certain mass, 4 times the atomic mass unit. And incidentally, let me define once again the atomic mass unit. Atomic mass unit is defined as 1/12th of the mass of the most abundant nucleus, most abundant isotope of carbon, which is carbon 12. So, carbon 12 is defined as having mass 12.00, and 1/12th of that is defined as 1 atomic mass unit, and its value is 1.66 into 10 to the power minus 27 kilograms. So, these 4 nucleons have mass 4 U, 4 atomic mass units, and when they bind together, they lose some energy. That means, they lose some mass according to the Einstein's equation. Therefore, the mass of the nucleus is slightly smaller than the mass of the combined mass of the nucleons, and this difference is known as mass defect. And the larger the mass defect, more solidly are these nucleons bound together. Therefore, stabler the nucleus. Mass defect of a nucleus Az, for example, which A is the mass number, Z is the atomic number, is defined as delta m equal to AU. A is the number of nucleons into U, the atomic mass unit, which I defined just now. That is the mass of the combined mass of all the nucleons, and minus the measured mass of the nucleus Az gives the mass defect. And as I said, larger the mass defect, more tightly bound are the nucleons, and therefore, more stable is the nucleus. So, just as the mass of a nucleus is smaller than the combined mass of the nucleons because of the energy used in binding them together, the mass of an atom is also slightly smaller than the combined mass of the nucleus and the electrons, because electrons are bound to the atom, they are bound to the nucleus, and when they are bound they lose some energy in the process of binding. Energy loss means mass loss. Therefore, the mass of an atom is also slightly smaller than the mass, combined mass of the nucleus and the electrons. And the mass of an atom, say hydrogen atom, would be mass of a proton plus the mass of an electron minus the binding energy by c squared. Here we have given the mass defect of a few nuclei. You can see this is the mass number of protons, you can see this is the number of neutrons, and this would be the combined mass of all the nucleons, and this is the actual mass, and this is the mass defect. Difference between this and this is mass defect. That is how we define mass defect. Mass defect is the mass of all the nucleons, combined mass of all the nucleons minus the actual mass, the measured mass of the nucleus. What happens if we want a body to escape the gravitational field of the earth? This you must have done in class 11. We need to supply energy to the body, so that it acquires velocity equal to the escape velocity or escape speed. Similarly, here if we want to break a nucleus, we will have to supply energy equal to the binding energy, that is delta m times c squared. That is the energy we have to supply to the nucleus to break it, and the energy necessary to break the nucleus is called its binding energy, and it is usually expressed in terms of binding energy per nucleon. And here we have got deuterium, isotope of hydrogen, and its binding energy is 1.11 MeV per nucleon. Here we have got helium 3, whose binding energy is 2.58 MeV per nucleon, helium 4, whose binding energy is 7.07 MeV per nucleon, and similarly lithium, carbon and oxygen, their binding energy per nucleon is given. If you want to find the total binding energy, multiply by the number of nucleons. In this case, for example, the number of nucleons is 16, therefore, the binding energy would be 16 times 7.98 MeV. Take the example of lithium. Here lithium has 6 nucleons, and the mass defect we found in an earlier table is 0.042135 U atomic mass unit, that is delta m multiplied by c square gives us the binding energy. And how do we do that? 1 U, 1 atomic mass unit in terms of energy is 931.494 MeV. So, we can find the binding energy in MeV, and since there are 6 nucleons in lithium, therefore, the binding energy per nucleon is 39.25 divided by 6, which is 5.607 MeV per nucleon. So, that is how we find the binding energy. Take the mass defect, multiply by c square and divide by the number of nucleons in that nucleus. And now, we plot the binding energy per nucleon against the mass number. You see, in this graph, mass number goes from 0 to something like 250, and the binding energy, you can see the binding energy is maximum in this band. This band is with mass number 55 to about 65. So, in this band the binding energy is per nucleon is maximum. This means that this is the region of most stable nuclei. Nuclei on this side where the binding energy is decreasing they are less stable than nuclei in this band. On this side also the nuclei are less stable than the nuclei in this band, and therefore, there is a tendency for nuclei on this side to break into two nuclei, and both of them migrate towards this band, towards this stable region. Here the lighter nuclei combine, the process is called fusion, and the resultant nuclei have higher binding energy per nucleon. That means, they are more stable than the lighter nuclei here. So, on this side nuclei migrate towards this band by fission. On this side nuclei migrate towards this band of stable nuclei by fusion, and both fusion and fission give us energy, because the binding energy per nucleon is increasing. If it is increasing, that means that the energy is given out. The difference between the binding energy of this and this is given out, and that is the energy we get in fusion and fission. In this case, you may not be able to see the details of nuclei up to, let us say, mass number 20. So, just to show you that, I have plotted this graph, and I will point out a few things here. You see this is mass number 4, 8, 12, 16 and 20, and you can see that there are peaks at these mass numbers. That means, mass numbers divisible by 4 are more stable than mass numbers not divisible by 4. You see, this mass number 4 is more stable than these 3 and these 3. Mass number 8 is more stable than these and these. So, the mass number divisible by 4 is more stable than the mass number not divisible by 4. We shall see this later. Now, this is what I have been talking about, that on this side nuclei are unstable, on this side also nuclei are unstable. Therefore, here there are large nuclei, they break into smaller nuclei, and the product nuclei are both more stable than the parent nucleus. Here lighter nuclei combine to give a nucleus which is more stable, and this process is fusion, this process is fission. And in both cases, the binding energy per nucleon of the product increases, and the binding energy per nucleon we shall see of the product minus the binding energy of the reactants, that gives the energy which we get in the process of fusion or fission. Now, nuclear fusion is very important for us, because it is the source of energy which powers the sun and other stars. What happens is that 4 protons they combine and they form a helium nucleus, that is 4 hydrogen nuclei, they fuse to give us a helium nucleus. Helium nucleus has higher binding energy than the hydrogen nuclei, 4 hydrogen nuclei. Therefore, there is release of energy. In other words, we can say that the mass of the helium nucleus is smaller than the mass of the 4 protons put together, and the difference is released as energy. And we shall see this process is achieved in 3 steps. One hydrogen nucleus, that is proton, and another proton, they come together. How they come together I shall discuss in a moment, but they come together and they form a deuterium nucleus, which contains one neutron and 1 proton, and in the process a positronium and a neutrino, they are released, and energy of course is released. Then this deuterium takes another proton and becomes helium 3, releasing some energy in the process, and 2 of these helium 3 nuclei, 2 of these, they interact and they give us a helium nucleus. This is helium and 4 nucleons. This is helium. This is also wrong. This is also wrong. These are 2 helium-3 nuclei. 2 helium-3 nuclei, they give rise to a helium-4 nucleus, and 2 protons are released along with energy. That means, in all 6 protons are pressed into surface. 4 of these form the helium nucleus, 2 are released and they come back and join again in the process of this fusion, and lot of energy is released in the process. If you want to see an animation of this process, this is known as proton-proton chain, because protons are combining with one another, and if you want to see chain process, animation of the chain process, you can go to this website. Nuclear reactions are characterized by their Q values. Whenever a nuclear reaction takes place, there is a Q value attached to it. What is Q value? Q value is simply the energy released in the process. Q value is simply the difference between the combined mass of the reactants and the combined mass of the products, and the difference of course is equal to the Q value in terms of energy. The difference of mass multiplied by C square gives us the Q value. In this reaction, A plus B equal to C plus D, these are the reactants, these are the products, and the difference in the mass of the reactants and the products multiplied by C square gives us the Q value. Let us see this Q value in terms of the binding energy and the mass defect. We have seen Q is mass of the reactants minus the mass of the products, and we have already seen that in a nuclear reaction the number of protons and neutrons, this number remains conserved. So, we can write the Q value equal to the mass, that mass is equal to the number of the mass of the nucleons minus the mass defect, and here also the mass of all the nucleons, neutrons and protons minus the mass defect, and these two, they being equal, they cancel. Remember that number A, the mass number in any nuclear reaction is conserved, and this is mass number, this is mass number, the number of protons plus number of neutrons. So, that cancels, and therefore, we get Q value equal to the mass defect of products minus the mass defect of reactants, and we can convert this into binding energy, and therefore, Q is binding energy of products minus the binding energy of the reactants. All that you need to do is multiply this by C square, that is convert mass into energy. So, we know in the fusion reaction binding energy of the products is higher than that of the reactants. Binding energy is higher than that of the reactants. Let me remind you of this graph again. The products are going towards this band, their binding energy is rising. On this side also the products are going like this, their binding energy is rising. So, the binding energy in the process rises, and the difference between the final binding energy minus the initial binding energy gives us the energy or the Q value. Now, binding energy of a few nuclei, again this graph I have shown you already. So, let me show you again, because we are going to use it in calculating the Q value. As an example, we calculate the Q value of the last reaction of the proton-proton chain. What was the last reaction? Last reaction was 2 helium-3 nuclei combining to give a helium-4 nucleus and 2 protons. So, let us calculate the Q value of this reaction. So, for this we make use of the table here, the mass, the binding energy per nucleon for the helium is 2.58 per nucleon. So, multiplied by 3 gives the mass, gives the binding energy for the helium-3 nucleus, and since 2 nuclei are involved, so we multiplied by 2, and that is what we have done. So, this is the binding energy of the reactants, and this is the binding energy of the products, 7.07 into 4, that is the binding energy of the products. So, the difference gives us the Q value. 12.8 MeV is the energy released when 2 helium-3 nuclei combine to give us helium-4 nucleus plus 2 protons, and energy given out is 12.8 MeV. So, this is a difficult thing. In order to fuse, the 2 light nuclei of atomic number Z1 and Z2 must come within a distance of 10⁻13 meters. You see, at this kind of distance, two nuclei were never combined. If they have to combine, they must come within a certain distance, so that they can feel the force of one another. That means, they must come to a distance as small as 10 to the power minus 13 meters. At this distance, their electrostatic potential, you see we have two protons or two charges Z1 and Z2 to make the argument general. The potential energy then becomes Z1 Z2 E squared divided by A. A is the distance equal to 10 to the power minus 13 meter. So, that is the potential difference or potential energy between the two protons. That is the kind of repulsion they feel, and they must overcome this potential barrier to combine. You see, they were here at a distance of 10 to the power minus 13 meters. For further reduction in distance, they must overcome this potential barrier, that is the potential difference at a electrostatic potential energy at a distance of A. So, they must overcome this, and if you calculate, you can show that for this the relative kinetic energy of these two reactants, two protons for example, must be of the order of 56 into 10 to the power 6 K. That is, the temperature must be so high, so that the relative kinetic energy of two protons is greater or equal to this potential barrier. That means, you require such high temperatures for fusion, that is for two protons to combine. Now, we know in the sun we never have this kind of temperature. The temperature in the interior of the sun is 15 million degrees, 15 into 10 to the power 6 K. So, where do you get the kinetic energy, relative kinetic energy of the two protons to make them combine? Well, one of the ideas is that the tail of the Maxwell distribution, at any temperature there is a distribution of energies of particles, and the tail of this Maxwell distribution, this distribution is known as Maxwell distribution or sometimes Maxwell-Boltzmann distribution. In the tail there are particles which have high energy, and some of these particles can overcome the potential barrier. But even that is not sufficient. What is needed is the uncertainty principle. I have been emphasizing in the last few lectures on the importance of uncertainty principle of Heisenberg. Here is how it comes to our help. Even if the energy is not sufficient, this is the energy of the relative energy of the two protons, and this is the potential barrier. Even if this energy is not sufficient, there is a finite probability given by the Heisenberg uncertainty principle that they can tunnel, the protons can tunnel through the potential barrier and meet. So, that is how fusion reaction takes place. The energy of the two protons may not be sufficient, smaller than the potential barrier, but there is a finite probability that they can tunnel through this potential barrier and meet. Fission is the source of energy in nuclear power plants on the earth. Fission, use uranium 235 to break and give you the energy. However, the waste product of a fission power plant are harmful for the environment, because the waste products are also radioactive, and they remain radioactive for a very long time, and it is a difficult process to dispose of them off so that they are safe. Since nuclear fusion does not suffer from this drawback, attempts are now being made in many laboratories. In fact, for the last maybe 30-40 years, attempts are being made to produce sustained fusion, so that it could be used for power production. Fusion, not fission. Fission is not easy to handle. The waste products are difficult to dispose safely, and therefore, we are looking for a process of fusion that might work in the laboratory or on the earth to give us energy. And what is the process being looked at? Deuterium plus tritium would give helium nucleus and a neutron. That is the process being looked at. Pictorially, we have here the deuterium and the helium tritium. They come together, they are made to come together. It is difficult for them to come together. Again, because of potential barrier between them. So, you have to raise the temperature very high, so that they get enough relative kinetic energy to come together. That is another story, but we make them to come together, and then they fuse, they produce helium 4 and a neutron. This is all in theoretical realm. The actual process in some labs has been achieved for a very short time, but that is not enough for us. We need the process to be sustained over long time, so that we can get a lot of energy. And one advantage of this would be that it will be a cleaner source of energy, cleaner than the source than fission that we get in the modern nuclear plants. And we do not have to look for then also uranium and thorium. You do not have to look for that. You need hydrogen 2 and hydrogen 3 to work. Now, since the combined mass on the right is less than the combined mass on the left, energy equivalent of the mass difference is released. That is what I have been saying all along. And for the animation of this process, you can again visit this website. Another important fact that emerges from the binding energy curve is that nuclei with a multiple of 4, remember 8, 4, 8, 12 are generally more stable than others. I pointed out to you, the same graph here, 4, 8, 12, 16, 20. You can see that there, compared with their neighbors, they are more stable nuclei. So, nuclei with mass numbers 4, 8, 12, 16, 20, they are more stable than the other nuclei. In the next lecture, we shall continue with this stability of the nuclei, and we shall also see why protons and neutrons are both necessary for the stability of the nucleus. And the important thing is, we shall also discuss radioactivity, things like mean life and half life. In this lecture, we have concentrated on the binding energy per nucleon, because that helps us to find where the nuclei are more stable, and on one side the nuclei are quite heavy, they break into smaller ones, so that they approach this band. On this side, nuclei are very light, so they combine and they approach the band and become more stable. So, in this lecture, we have concentrated on the binding energy per nucleon, and in the next one, as I said, we shall continue with the stability of nuclei.